Welcome to Snoozecast, the podcast designed to help you fall asleep. Find us on snoozecast.com and follow us on Instagram @Snoozecast to find behind-the-scenes content. If you enjoy our show, please write a review on the Apple Podcasts app. Also, share us with a friend. Please know that we read and appreciate every single one. If you would like to get an email once a week with upcoming sleep stories and other news, subscribe to the Snoozeletter at snoozecast.com. This episode is brought to you by our Patreon supporters and by a London particular. Tonight, we'll read excerpts from Meteorology, the Science of the Atmosphere, by meteorologist Charles Fitzhugh Talman, published in 1922. The word meteorology, stemming from the ancient Greek, means the study of things high in the air. Though study of meteorology dates back millennia, significant progress did not occur until the 18th century. Prior attempts at prediction of weather depended on historical data. It was not until after the elucidation of the laws of physics, and more particularly, the development of the computer, allowing for the automated solution of a great many equations that model the weather in the latter half of the 20th century, that significant breakthroughs in weather forecasting were achieved. Let's get cozy. Close your eyes. Relax your body under the softness of your bed. Now, take a few deep breaths. Meteorology is the science of the atmosphere and its phenomena, including weather. Nowadays, when we speak of a meteor, we generally mean a shooting star. But formerly, this term was applied, and it still often is in technical literature, to a great variety of phenomena and appearances in the atmosphere, including clouds, rain, snow, rainbows, and so forth. That is how the science of the atmosphere came to have its present name. Meteorology is not a branch of astronomy. These two sciences are as different from each other as zoology is from botany. They are both founded on physics, and they overlap each other to some extent, just as every science does certain others. But if you want information about the atmosphere, weather, and climate, an astronomical observatory is not the place to seek it. While if you wish to make inquiries about comets, sunspots, eclipses, standard time, or the date on which Easter fell in the year 1666, do not apply to the Weather Bureau. In the city of Washington, the government maintains an astronomical and timekeeping institution known as the Naval Observatory, and it maintains in the same city the central office of the United States Weather Bureau. The two establishments are a mile apart in space and nearly a whole library apart in the subjects with which they are concerned. The fact that their functions are persistently confounded by the public indicates the necessity of writing this preface to a popular book on meteorology. The Anatomy of the Atmosphere. Two quite different conceptions of the substance called air are current in the world. One has prevailed from time immemorial. The other is wholly modern. One is the popular view, the other the scientific. Ancient philosophers regarded air as one of the four elements of which all things were supposed to be made. Average humanity, though it did not concern itself with philosophy, must have begun almost as soon as it realized the existence of air at all, to think of it as something that, however it changed its state from hot to cold, dry to moist, pure to impure, was fundamentally uniform, a single entity. Certainly this idea is in full vigor today. The air that we breathe, supply to our fires, stir with fans, pump into bicycle tires, fly in, the air that asserts its independence of our will in the wind and the weather, gives us the impression of individuality. We instinctively rank it with water among the simple, definite things in the repertory of nature. Even the man of science often finds it convenient to discuss and deal with air as if it were a single substance, but he is well aware that it is nothing of the kind. He knows that it is, in fact, a jumble of gases having very different properties. Some are heavy, others light. Some are chemically very active, others extremely inactive. Some are abundant, others very rare. These gases constitute the Earth's atmosphere. Other planets have atmospheres that are quite different in composition from ours. The Sun itself has a very complex atmosphere. The Earth's atmosphere is then a collection of gases which are mixed but not chemically combined. Some of them are themselves chemical compounds. Each of these gases behaves very much the same as if the others were not present, and each of them has its separate business to perform in the economy of nature. For example, a tree draws upon the store of carbon dioxide gas in the atmosphere to build up its tissues. Presently, the tree is cut down and its wood is burned for fuel. In this process, a different atmospheric gas is brought into play. We often say that the air supports combustion, that we supply air with a bellows to make a fire burn more brightly. But it is not the air as a whole that enables things to burn. 4/5 of the atmospheric substance takes no part in the process. We burn with oxygen alone. So it is with breathing. Oxygen, and not air, constitutes the breath of life. Near the surface of the earth, the proportions of the more abundant gases mixed together in the air are remarkably constant. Of course, almost any gas may be found locally and occasionally in the atmosphere, but there are several that are always found wherever a refined analysis of the air is made, and others that are generally present. The following is a fairly complete list. Nitrogen, oxygen, water vapor, carbon dioxide, hydrogen, helium, neon, krypton, xenon, ozone, hydrogen dioxide, ammonia, and other compounds of nitrogen. Cloudland. One of the things a tea kettle is good for is to provide, by means of the little cloud seen at its nozzle and erroneously called steam, an example of what happens when the invisible gas that is truly steam or water vapor is cooled below its dew point in the free air. This cloud has, however, been the starting point of a vast number of halfway explanations. A generation or so ago, physicists were content to say that aqueous vapor turns to drops of water in the air merely on account of being cooled. The question of how the drops get their start, or why the moisture forms drops at all, does not seem to have troubled them. Another important fact about water drops in the atmosphere has come to light within the last half century. Since water is much heavier than air, meteorologists of an earlier generation were puzzled by the fact that the drops in clouds apparently float instead of falling to the ground. In the attempt to account for this supposed floating, bygone authorities assumed that the drops were hollow vesicles, like little bubbles. This assumption was eventually disproved by the optical phenomena exhibited by the drops, as well as on other physical grounds. Moreover, it is now known that a cloud never really floats, though the rate at which its constituent particles fall with respect to the air is generally very small, on account of the resistance they encounter. Thus, a very slight upward current usually suffices to maintain the altitude of a cloud, or even to increase it. The speed with which a drop falls increases with its size. Hence, large drops may fall rapidly from great heights all the way to the ground, constituting rain. But in a great many cases, such drops evaporate on falling into warmer air below the cloud level, and thus the lower surface of the cloud remains at about a constant height. Town fogs, such as the famous London particular, usually consist partly of smoke. Dense fogs of this sort occur when the conditions of the atmosphere are such as to cause the smoke to hang low over the city instead of being dispersed. These fogs constitute a serious economic problem. Thus, it is estimated that they cost the people of London upwards of $500,000 a year due to extra lighting, damage to vehicles, loss of business, etc. Since marine fog is also a source of enormous loss through causing delays and accidents, and since fog along air routes is the greatest of all obstacles to successful aerial navigation, it is no wonder that much ingenuity has been devoted to the attempt to disperse fog artificially. Electric discharges have been successfully used for this purpose on a small scale. Clouds, though they are nothing more than masses of fog situated at some distance from the earth, are susceptible of a classification according to shape and texture that is not applicable to fog. Among the billions of human beings who, in all ages, have amused themselves by discovering pictures in the clouds, it would be remarkable if a good many had not, from time to time, conceived the idea of reducing these pictures to a few general types. according to a note published a few years ago in the Quarterly Journal of the Royal Meteorological Society, there is some reason to believe that an elaborate classification of the clouds was in use among the ancient Hindus. A passage quoted from an Indian work of the 4th century BC says, "3 are the clouds that continuously rain for 7 days. 80 are they that pour minute drops, and 60 are they that appear with the sunshine." In the Occidental world, however, we have no record of any attempt to classify the clouds prior to the year 1801, when the following classification was proposed by the French naturalist Lamarck. Cloud sweepings, clouds in bars, dappled clouds, grouped clouds, veil clouds, clouds in flocks. In 1803, the English meteorologist Luke Howard published the system of classification that, with some additions and modifications, is now in general use. This system is based upon 3 fundamental forms: fibrous or feathery clouds, cirrus; clouds with rounded tops, cumulus; and clouds arranged in horizontal sheets or layers, stratus. Intermediate forms are described by compounding the names of the primary types. For example, cirrocumulus, cirrostratus. The rain cloud is called nimbus. Howard's classification was quickly adopted in all countries. His definitions were translated into German by no less than Goethe, who, in his enthusiasm over Howard's achievement, wrote a poem about it, and also a separate poem about each of the principal types of cloud. There are 10 principal types of cloud in the international classification, and the name of each type as an official abbreviation, a great convenience for those who record the clouds from day to day. The following definitions, translated from the French text of the International Cloud Atlas, have been published by the British Meteorological Office. 1. Cirrus. Detached clouds of delicate appearance, fibrous, thread-like structure, and feather-like form, generally white in color. Cirrus clouds take the most varied shapes, such as isolated tufts of hair, i.e., thin filaments on a blue sky, branched filaments in feathery form, straight or curved filaments ending in tufts, and others. Occasionally, cirrus clouds are arranged in bands, which traverse part of the sky as arcs of great circles, and, as an effect of perspective, appear to converge at a point on the horizon, and at the opposite point also, if they are sufficiently extended. Cirrostratus and cirrocumulus also are sometimes similarly arranged in long bands. Certain forms of cirrus are called mare's tails. The long bands crossing the sky, as just described, are known as polar bands or Noah's Ark. 2. Cirrostratus. A thin sheet of whitish cloud, sometimes covering the sky completely and merely giving it a milky appearance. It is then called cirronebula or cirrus haze, at other times presenting more or less distinctly a fibrous structure like a tangled web. This sheet often produces halos around the sun or moon. 3. Cirrocumulus. Mackerel sky. Small, rounded masses or white flakes without shadows, or showing very slight shadow, arranged in groups and often in lines. 4. Altostratus. A dense sheet of a gray or bluish color, sometimes forming a compact mass of dull gray color and fibrous structure. At other times, the sheet is thin, like the denser forms of cirrostratus, and through it, the sun and moon may be seen dimly gleaming as through ground glass. This form exhibits all stages of transition between altostratus and cirrostratus, but, according to measurements, its normal altitude is about 1/2 that of cirrostratus. 5. Altocumulus. Larger round masses, white or grayish, partially shaded, arranged in groups or lines, and often so crowded together in the middle region that the cloudlets join. The separate masses are generally larger and more compact, resembling stratocumulus in the middle region of the group, but the denseness of the layer varies and sometimes is so attenuated that the individual masses assume the appearance of sheets or thin flakes of considerable extent with hardly any shading. At the margin of the group, they form smaller cloudlets resembling those of cirrocumulus. The cloudlets often group themselves in parallel lines, arranged in one or more directions. 6. Stratocumulus. Large, lumpy masses or rolls of dull gray cloud, frequently covering the whole sky, especially in winter. Generally, stratocumulus presents the appearance of a gray layer broken up into irregular masses and having on the margin smaller masses grouped in flocks, like altocumulus. Sometimes this cloud form has the characteristic appearance of great rolls of clouds arranged in parallel lines close together, rollcumulus. The rolls themselves are dense and dark, but the intervening spaces, the cloud, is much lighter, and blue sky may sometimes be seen through them. Stratocumulus may be distinguished from nimbus by its lumpy or rolling appearance, by the fact that it does not tend to bring rain. 7. Nimbus. A dense layer of dark, shapeless cloud with ragged edges from which steady rain or snow usually falls. If there are openings in the cloud, an upper layer of cirrostratus may almost invariably be seen through them. If a layer of nimbus separates in strong wind into ragged cloud, or if small detached clouds are seen drifting underneath a large nimbus, either may be specified as fractonimbus. 8. Cumulus. Woolpack cloud. Thick cloud of which the upper surface is dome-shaped and exhibits protuberances, while the base is generally horizontal. These clouds appear to be formed by ascensional movement of air in the daytime, which is almost always observable. When the cloud and the sun are on opposite sides of the observer, the surfaces facing the observer are more brilliant than the margins of the protuberances. When, on the contrary, it is on the same side of the observer as the sun, it appears dark with bright edges. When the light falls sideways, as is usually the case, cumulus clouds show deep shadows. True cumulus has well-defined upper and lower margins. But one may sometimes see ragged clouds, like cumulus torn by strong wind, of which the detached portions are continually changing. To this form of cloud, the name fractocumulus may be given. 9. Cumulonimbus, the thundercloud. Great masses of cloud rising in the form of mountains or towers or anvils, generally having a veil or screen of fibrous texture, false cirrus, at the top, and at its base a cloud mass similar to nimbus. From the base, local showers of rain or snow, occasionally of hail, usually fall. Sometimes the upper margins have the compact shape of cumulus, or form massive heaps round which floats delicate false cirrus. At other times, the margins themselves are fringed with filaments similar to cirrus clouds. This last form is particularly common with spring showers. The front of a thunderstorm of wide extent is frequently in the form of a large, low arch above a region of uniformly lighter sky. 10. Stratus, a uniform layer of cloud, like fog, but not lying on the ground. The cloud layer of stratus is always very low. If it is divided into ragged masses in a wind or by mountain tops, it may be called fractostratus. The complete absence of detail of structure differentiates stratus from other aggregated forms of cloud. We have given the foregoing official definitions and descriptions in full in order to aid the listener as much as possible. So far as verbal information goes, in learning to call the common clouds by their names, good pictures are, of course, an essential part of this process. And apart from those that illustrate the present text, many collections of such pictures are easy of access. Some may be obtained free or at nominal cost from the Weather Bureau in Washington Meteorological Office in London. The International Cloud Atlas, 2nd edition, Paris, 1910, is now out of print, but may